everyone. We are Jean-Baptiste Not and Anadine. We are software engineers from Criteo. For those of you who haven't heard of Criteo, our core business is personalized retargeting, which means that we're displaying the right ad to the right person at the right time. Now, the center of our software are a set of prediction and recommendation algorithms that feed on data we collect from our client advertisers or publisher websites. And back in the day, a few years ago, that kind of data was stored in SQL servers. But as it grew every day, it became quite obvious that we need a solution that scales. And that's how we joined the Hadoop world. Currently, Criteo has 6 data centers serving 4 continents and more than 120 billion requests per day. So imagine the volume of data that we collect every day and that we have to store and process. Scaling our infrastructure is not the only way we do that. We also have on board the best software engineers. And as you can see, we're still looking for new talent. So apologies for the cheesy flyers on the chairs, but we left in a rush, so we got what HR gave us. But what's to remember from them is Criteo Labs, which is the website where you can find more information for our R&D team and also job openings. Back to the infrastructure. The constant and rapid growth of business forced us to scale from a 12-node cluster to several hundred and counting in quite a short period of time. I can tell you that the ride was not smooth, as cluster administration makes no exception from Murphy's Law. And I will further let Jibé present you with the problems that we faced on the way, and he'll also share with you the precious lessons learned from it.
Thank you. So, is the mic working? Yeah. So I will tell you actually the story of a very fast-growing and very successful startup, which happens to use Hadoop. Growing means you have increased volume. The fact that it's being successful means you have cash to actually pay for your infrastructure. And the fact that it's a startup means that you are very constrained in time and in manpower. So what happens on Hadoop? On Hadoop, the proof of concept is very easy. But once you start to gain traction, everything will get very fast. So how fast? So 2.5 years ago, 12 nodes. 2 years ago, 150 nodes. Today, around 600 nodes. And by the end of the year, 1,000 nodes, more than 1,000 nodes. So why is the growth so fast? Well, dear brothers of the Elephant Church, as soon as you start using Hadoop, you hit a virtuous circle. So first, your development teams will gather know-how on the platform. Then, I don't know if some of you remember the guy on the Teradata presentation, the handsome guy with the open collar. Well, that's not you. That's the BI analyst. And the BI analyst wants more data. And the more they get, the more they ask for. So this is another way to grow the cluster. Another, from the operation point of view, another very interesting thing is that Hadoop will be seen as a platform to consolidate various ad hoc data processing tools that you had splittered around various parts of your architecture. And of course, because you're using Hadoop, your business will boom, you will get rich, you will be able to treat yourself as a royalty, and you will have organic growth of your data volume. So in this scheme of things, what happened at Criteo is that you, meaning the admin of the Hadoop cluster, risk being the bottleneck. And what I'm going to tell you is how you make Hadoop administration scale so that you're not the bottleneck. So you need to scale. And scaling means two things. First, scaling infrastructure management. For this, you need to automate administration. This will be the first point in the topics covered. You need to tune the full stack to get the most out of your infrastructure, because every % you gain is a penny saved. And among this tuning that you need to do, there's a special case for networking. And there's a special case for networking because problems in networking are highly non-linear, so you really don't want to hit the wall. We did hit it, and it hurt. And once you've scaled infrastructure management, you will want to scale infrastructure usage, and that's what we call internally and everywhere else, I guess, multi-tenancy. You will have to manage resource contention, because usage for your cluster will probably outgrow the pace at which you can scale it. So there will be contention for resources, meaning contention for storage resources, meaning contention for computation resources. But once you've integrated those problems, and we'll show you how and what you need to be done, then you can open a Hadoop as a service to your clients from everywhere in your data centers. And that opens a whole lot of possibilities. So let's switch to the first thing that we think we did sufficiently well to talk about it, is administration automation. So the first rule is don't do anything by hand, because you will hurt your hands if you have to delve individually into 1,000 servers. You have to build once, run forever. You have to release manage every change you make. This is very important. And you have to automate the full stack, from OS installation to OS tuning to service management and then service monitoring. And another rule that we impose ourselves is to be independent on vendors. So I know that a lot of people here will try to sell you Cloudera Manager or Ambari or solutions like that, which shows to make things in an independent way from vendors. First, because there's vendor lock-in, and then because every click you do on an interface is usually not tracked and not release managed, and you want this tractability. So, in short, what we want to do is a traditional DevOps motto. We want to treat infrastructure as code. And in order to do this, we used Chef. Because it's a Turing language complete, you can automate the full stack. You can, because it's code, you can release manage it. And it's completely vendor and distro neutral. So actually we're currently using Cloudera, but we made tries of the Hortonworks stack, which we plan to switch to, and it really was a breeze to switch from one to the other. So beyond the statements of intent, what did we do actually? So we reach a state of rack and load. What we expect currently from production is from them to, from traditional production, which is now kind of hosting, we expect them to rack machine, set up the networking gear, and from then on, as soon as they press the power button, the machine is ours, meaning we take care of it, and by we mean the chef recipes that we developed. So in our current scenario, 3 hours after a machine boots, it appears in the cluster. And the reason why it takes 3 hours is that it has to format the hard drives, which basically takes 2 hours and a half. So there's around 30 minutes of chef setup. All of this system was developed by the Hadoop team for the Hadoop cluster and is now currently being extended to the whole company. We have something very Hadoop specific, is in that we use a Diskless system, operating system. Why are we doing this? So yes, I didn't do the slide. Why did we choose a Diskless system? Well, when you buy hundreds of machines, what you really want to do is to maximize storage density. You really want to fill those 14 slots with 3 terabytes drives. What happens then if you want to install an OS on them? Well, you will probably take 2 of them, partition them specifically, and have an OS installed in RAID 1 mode, for instance. But for once, you break the nice symmetry of your system. You have now 2 specialized disks. Secondly, what happens is that in case of a really bad failure, even with RAID 1, you will end up with an unusable system. Sorry. We really don't want to break symmetry. So the Diskless system appeared as a natural choice. There are more pragmatical constraints. Diskless is a very tough thing to manage because it makes constraints very explicit in your system. For instance, when you're on a Diskless system residing in RAM, what you will have to tackle is, for instance, remote logging, which you will have to do, and which is a good thing to have, but this makes it compulsory. And for instance, if you look at the Facebook, there was a Facebook presentation about how they mounted temp in a temp FS. They had to do it for performance reasons because there was contention between I/O on the system disk and I/O for the Hadoop. Well, we never had the problem because from the beginning, temp was mounted in temp FS. So it makes sense. It may sound completely irrational or not really pragmatical, but in the end, it makes sense. The cost of it is around 2% of the RAM on our nodes, so it's pretty acceptable. So you can actually fit a Hadoop system in 2 gigabytes, no problem. So that's for the, yes, and there's also a very pragmatic reason is that the 150 nodes cluster we had initially was operated in a normal way by production, and what we observed is absolutely huge failure rates for the disks containing the systems. But this was more a remark in hindsight, but after the fact it proved our point. So what's left once you know how to rack and once you rack your systems as fast as this? So yes, I will just skip over this slide. So we have standard PXE booting and everything's done by Chef from inventory to firmware upgrades and then to service deployment. What's left? Well, not much really. You have evolutive maintenance to take care of, meaning basically version bumps for CDH version bumps. Usually the cluster takes care of itself, meaning if you have a node going down, if you have a disk on a node going down, you don't really have to react by the minute or by the hour, or even you can just leave the system as is, it will recover easily. The issue you have to take care of is when you have a slow performing host. It's not really a problem for throughput, but usually it extends the duration of your jobs hugely because you will have one outlier mapper lasting much longer than the others. So it will hurt performance and it will be a problem for interactive users like Hive. And same problems with flaking hosts, which appear and disappear. They can cause problems. There are risks to HDFS because the blocks on them are not totally replicated. So you can get into a situation where two nodes are flaking, and if a third one goes down, then you have missing blocks. How do we manage this evolution? Well, first, for maintenance, evolutive maintenance, we have a pre-prod cluster and a prod cluster, and we always rehearse state changes from one version to another on the pre-prod cluster, and then do it quickly on the prod cluster in order to accumulate the experience. And you will probably be faced with progressive or blackout maintenance operations. So I guess progressive maintenance is progressing by the day. We are not quite up to date. We are using CH 4.6.0. But our experience is that progressive rollouts of updates usually degenerates into blackouts and offers degraded performance while you're doing the maintenance. So we prefer to have a blackout period of, say, 1 hour during the day where we do the maintenance operation when we need one. They're very infrequent. We're talking about one operation every 2 months maybe, so it's pretty reasonable. For the rest, meaning configuration change deployments, for name nodes we have HA enabled, so you can activate your new configuration on the backup name nodes, switch your name nodes, and activate on the former active name nodes. It's very easy to do. It's a bit more painful on the job tracker, but it's doable. And for data nodes, we just do a running restart of the data nodes. So let's have a look beyond maintenance to monitoring. Of course, you need to be aware of what happens on your cluster, even if it self-heals and takes care of itself. Especially, you don't want to be a clown and have users reporting failures before you do. And what typical Hadoop users does is he launches its job and then goes to the job tracker and then hits refresh. So you want to monitor your job tracker interface. You really want that. But more seriously, what you absolutely need to do is to monitor FSIMers checkpointing. So I won't go into the details, but this is the consolidation operation on the state of the name node. So in a non-HA scenario, there's a dedicated server to do this. In an HA scenario, you have the standby name node doing it. And actually, your cluster can function very well without any checkpointing on, until you fill up the disk for your name node with backlogs of edits. Your name node crashes, and then when it boots again, it has to replay 3 months of edits, which takes like 24 hours. So we had the experience. It was not a good one. So yes, watch for FSImage checkpointing. There's a blog entry by Cloudera talking about it, but really, it's really important. Yes, and you can, of course, monitor HDFS usage, standard stuff. So Hadoop is only a part of your system when you have your own cluster. And basically, you have to do tuning along the whole stack. Because what you will observe is that standard network infrastructure is not good for Hadoop. Standard Linux kernel configuration is not good for Hadoop. And standard Hadoop configuration is not good for Hadoop at scale. So, yes, there's another thing that is not working at scale. It's the rest of your infrastructure. So when you have 400 coordinated nodes doing the same thing, you will basically be a DDoS to your infrastructure. So when something goes wrong with Hadoop, when you have performance problems, the first place to look for bottlenecks is outside of Hadoop. So for instance, we're still using layer 2 switching between the nodes, and we had ARP storms, and we had to increase ARP retention in order to bring down the number of ARP requests in the layer 2 switches. You want, for instance, to use local caching whenever available, for instance, an SCD to cache DNS requests. Once you've done this, you will have to tune the kernel. So basically, you want to increase throughput. You want to increase disk usage throughput. So for writes, it's very easy. We have the buffer cache. It fills up sometimes, and you flush to disk. For read, the only intelligent thing to do is to do dumb prefetching of the data, which is called read ahead. The default read aheads are really small in Linux, so you need to increase them, and you will actually increase your I/O throughput quite a lot. Yes, I forgot to mention that you see a lot of artificial benchmarks about the clusters. So I cannot tell you exactly how much this brings, because in reality, benchmarking a busy cluster is just impossible. It's even impossible from day to day, because from day to day we have huge variation in the amount of data, depending on if we're on the weekend, if we're on weekdays. So it's very, very difficult to really benchmark a Hadoop system, running a Hadoop system. There's something which is memory bandwidth. It's very well known, very well documented. You want to disable THP compaction, so transparent huge pages compaction by the Linux kernel, which is activated by default on CentOS, which is the OS we use. And for networking, also you may want to switch on jumbo frames. It reduces the interrupt load. So as far as Hadoop itself is concerned, so this is an excerpt of our Chef configuration files. So you change the value here, it's deployed automatically in the cluster. And what will you need to watch for? So the main point probably is to adjust log settings. By default, the log settings are hugely verbose, and you just don't realize it until you see the stream of data coming out of your name nodes. It's a huge performance bottleneck, actually. You probably want to increase some handler counts for job trackers, name nodes, data nodes. You don't want to be a pig, but you want to raise the defaults. You probably want to, so the name nodes, you can activate the different thread pools for standard HDFS clients, separate from the data node pool. It's very useful also for firewalling your cluster, for instance. If you don't want a user to have access to the internal service handlers, then it's a way to achieve this. It gives you much better. It will give you much better throughput for your HDFS clients. And you have to watch out for checkpointing loops. So high availability is nice, but it has quite a few downsides. One of them is that every HDFS client will first try one of the name nodes, and the other, if the first one does not respond, or tells him that it's currently the standby name node and it has to go to the other. Except that this response is very slow to come if the standby name node, as it does frequently, is checkpointing. And then there's the second problem is that the order in which the name nodes are tried is actually fixed. So you can get into a situation where you have so many edits going on in your cluster that checkpointing will take place very frequently. The standby name node will be very unresponsive to clients, and they will basically spend all their time waiting for the standby name node to tell them to go to the other name node. So watch out for this. And for job latency, it's really killer. So the day you expand your network cluster beyond the rack is the day you'll hear your network engineers yell at you. Why? Because contrary to the usual pattern of a web shop where you have a nice fat tree which is completely unscalable, to optimize your network traffic from and to the internet, which is usually called north-south traffic, you now have a system which actually uses the network as a bus. It's like a traditional HPC context, except the bus, where usually in HPC you spend a lot of time tuning this, is replaced by commodity hardware, which means networking gear. So it's east-west communication across machines rather than to and from the outside. And what we had to do is to overlay onto our standard model a meshed architecture to allow for this east-west traffic to be handled gracefully. So that's it, and that's something you need to plan ahead, really. Yes, and yeah, a word about layer 2, layer 3. We're still at layer 2, but we know that it will probably won't scale beyond 1,000 nodes, so we are thinking of going layer 3 for the routing. Okay, so when you talk about network topology, of course, Hadoop is aware of network topology. It's very well covered. You can do without it for starters, but as soon as you move beyond the rack, you have to do it for performance reasons, for reliability reasons, of course, and for maintenance reasons. It's very useful, actually. So at some point in our DCs, we didn't have enough room to grow the cluster, and we had to move the cluster. Well, we did that rack by rack, basically without interrupting the service. Probably ended up with the guys in Amsterdam here, being so tired that we had to move 2 racks at a time, but you can actually do it, and it's very useful. Okay, now that we have covered the basic infrastructure, let's talk about accommodating lots of very real users. So Hadoop begs to be a shared resources. We have only one cluster and we want to keep it that way. We may expand and have several clusters, but we won't have application-specific clusters at Criteo for now. A shared resource means you have to accommodate contention in the resources. So for storage, it's easy enough. You have quotas. So they come with a downside of their own, in that they can actually break checkpointing. We had quite a few checkpointing problems because of quotas. You can get into a situation where your edits don't replay nicely because of quotas. And for resource contention, you want to fine-tune scheduling. And because it is a user-facing thing, the users will be very vocal about it. They will spend their time tracking how their jobs perform, what their latency is for the jobs, and they will complain a lot if they see one mapper slot which is available and they can't use. So my recommendation would be to just use capacity scheduling. This is recommended in a very good blog post by a Hortonworks engineer. And why capacity scheduling rather than fair scheduler? Because in the fair scheduling world, it looks like you have a giant, infinite set of resources, and you just have a weight. And everybody wants a weight superior to his neighbor. When you use capacity scheduling, you embody in what you tell to your people in the interfaces the fact that whenever you want to dedicate more resources to a user, you have to take them from another. And from then on, it becomes a management problem and a politic problem, and you don't have people coming at you and asking for more resources because it's not extensible. Also, it helps with accountability because, of course, you want to enforce limits, but you want to have accountability. You want to know who is using what. So yes, we have a set of graphite dashboards. So this is shown for mappers and reducers. I won't go into the details because it's deprecated by Yarn now. So, so in a real-world situation, we actually do metrology on our clusters for IGFS usage, for MapReduce usage, and for mappers and reducer usage in order to fine-tune the ratio between mappers and reducers. Again, this is moot in a yarn context. Let's talk a bit about security. Once you realize your company's most valuable data, for it's just billing, has landed on a Hadoop, once after stellar growth you want to go IPO, is the time when you realize that the only security you have is through obscurity. And this is the time for acting. But you can actually plan ahead for this, because this is a huge beast. So security is two things. You'll know this. It's authorization and authentication. So for me, there's no question yet. You must not run a cluster. I think it's possible. You must not run a cluster without authorization. Authorization means I say to the name node, hello, I'm Jean-Baptiste, and I want to delete these files. And the name node says, oh, you don't have the right to delete these files. Fine. But then, in a standard situation, you can say, hi, I'm now the admin of the cluster, please delete these files. And the name node will tell you, go ahead, delete these files. So the second part in security, and the most problematic, is authentication. That is making sure that I am who I say I am. So, so basically, authentication is handled through Kerberos. So I have only good things to say about Kerberos. This is exactly the kind of old technology that you want to learn. Probably everything is done right in Kerberos and fits nicely in all environments. So at the end of the day, when you get it working correctly, it's probably the single sign-on technology you want everybody to use. It's not super easy to set up, but there are very, very good documentation from Cloudera. If you just follow it step by step, you'll get into a working situation. Using Chef, you can actually automate most of the tedious tasks of creating principles for your nodes. But it's less easy to actually integrate into IT. So you will have to need close ties with your IT department so that you ensure that the user experience is flawless. But once it's working, it's just excellent. You log into Windows, you just go to the job tracker page, and you're done. You are authenticated as yourself, and authorization is correctly applied. So what is on the slide? Yes. So we followed basically Cloudera's recommendations, meaning dedicated KDC, because you will have to create lots of principles in your KDC. You will have lots of loads on your KDC. And then you need to interface with the rest of the IT with cross-ring trusts. And this allows you, that's what we have, to delegate user management to your IT. So we delegate actually user authentication, but we still manage user authorization. We've not yet plugged into LDAP, which can be done, but so it's a choice not to do it for now. Once you've done this, once you've secured your cluster, once you've made sure that there was accountability and there was confinement of users, then you can offer your cluster as a service to your users. The model of having a standard SSH gateway to access your cluster just does not scale. So you want to open up the interfaces. The first thing that you want to open up is access to the Datastore. So a very severe limitation of Hadoop for now is that it does not offer a standard POSIX-like interface to the file system. But it does offer HTTPFS. Which is much more lightweight than the Java client, which is very heavyweight if you have lots of files to transfer to Hadoop. So it allows us to do data injection, data reads with a simple curl, even from C# code, and we do it with Kerberos activated. And currently we are streaming into the cluster with HTTP, only 4 HTTP-fast gateways. We stream an average of 200 to 400 megabytes per second of logs into the cluster. And we can have peaks that peaks at 1.6. We recorded peaks at 1.6 gigabytes per second into the cluster. So it's quite high throughput, and it just works. If you do a many-to-many scenario, you will get high throughput. A last word about file formats. You will hear a lot of talk about org files, and then Claudia will talk about Parquet formats optimized for Hive. What we do at Criteo, and we do this on the petabyte scale, is that we use a baseline JSON file and we compress it with gzip. And it's good enough for our uses. Actually, the Parquet developers that are hiding at Criteo have a very difficult time on a busy cluster to show benchmarks that would prove that Parquet is faster than baseline JSON. When you're IO bound, it just not really matter which formats you're using. Yes, so this is a case of don't try to optimize too early, don't go to binary formats. You will have the same density with gzip compression. You could maybe go faster with a binary, slightly marginally faster with a binary format, but gzip on JSON is good enough, and it gives you much more flexibility than binary formats. And I think that's it. So there's 4 minutes for questions. Otherwise, you can go and have lunch. If anybody's interested in questions, then please use a mic. Thank you.
Thank you. It's a very simple question about the format you've just mentioned. gzip is not splittable, so is it an issue in your case?
No, so we use, you'll know better than me, we use pale files, and we've upped it has nothing to do with the question, but we upped the default block size to 256 megabytes. So basically, when files are written directly into HDFS, not splittable means you have a mapper for the whole file. And then we basically just have a job which consolidates this into a pale file, which takes care of making sure that every block you have is under 256, is under your block size. Okay. So you actually get the same benefits as the splittable format by going through pale files.
Okay. So basically, does this work? JSON is the data format, and gzip compression is applied through pale, which is block aware. So we don't have that problem. And you can have multiple mappers feed on the same file without a problem and everything, just by using pale. I'm not the biggest advocate of pale, but I have to admit that it facilitates a lot of things. Besides the input scenario, when you want multiple mappers to fit on the big file, you can also have the use case, your job has 200 reducers, so it outputs 200 files. So the future job will require a lot of mappers for almost nothing, just to read the start, read, end. In which case, the end of the job, pale has a consolidate option, which appends lines to existing block and consolidates the file into the predefined format, which is 260 by default, 256 megs by default, but you can tune it if you need.
Okay, thank you.
No more questions? So I guess we are through. Thanks for your attention. Have a nice lunch.